Okay. So yeah, we'll talk about iteration today. I found it kind of somewhat helpful to try to sort of like think about iteration in a similar way to functions, and to draw some sort of an analogy. I don't know if it's exactly right, but to think that iterations is kind of to functions, what functions are to like copy paste code. So the idea is that when you're repeating the same code, let's say 3 times, the suggestion is to write a function so that you're not copy pasting the same code. And similarly with iterations, if you're doing a very similar, like running a very similar code, a similar function multiple times, maybe you should consider sort of the per package and iteration to sort of simplify that code so that if you want to change something, you change it in just one place rather than, you know, finding every other place that it's been used. And yeah, and the same sort of, I guess like the rules of thumb still apply, or like the intention behind it still applies, so that like if you have this more sort of succinct way of writing your code, then it becomes, it makes your code a bit easier to read and follow. But you need to be able to sort of speak this language of like compact representation, I guess. So the first part of the book talks about for loops and sort of a starting point. So like in the first example, we have a data frame with 4 columns, each of them with like 10 values from a random, sort of randomly picked from normal distribution. And if you wanted to calculate, let's say, median of each column, we could sort of do it one by one, or we could sort of iterate through each of the columns of the data frame and save it in an output vector that we have defined as a starting point to then get this output of basically the median of each of the columns. Later in the chapter, we learn how to sort of think about this general formula and how this can be translated into per packages, basically. So the first exercise was basically seeing if we can write for loops to do some relatively simple things. So question 1 is asking us to compute the mean of every column in empty card data frame. For question 2, yeah, let's just do question 1. So for these, I've sort of assigned the data frame into a generic variable name just to make things a lot easier to see, like the commonalities between them easy to see. So just like in the example given in the book and like the formula, if you will, given in the book, first I've created my output, which is a vector of doubles because I'm calculating the mean. So I expect to get doubles of the same length as my data frame and like the number of columns in my data frame. And for each of the columns, I'm going to calculate the mean. And before I do that, I also wanted to preserve the name. So if we actually, let me, so if we look at our starting point, we basically have the car name and then a number of variables about each of these cars, and we want to calculate the mean. And I wanted my final result to preserve the name. So I wanted to get basically mean and then MPG, whatever, CYL, etc., all of them. So I also gave my output the names of my data frame, which are the column names. And then for each column name in my names of my data frame, I said output with that name is the data frame where I pulled the column name and calculate the mean. So this gives me an output like so, where I have, well, it's not really displaying that well. Oh, 1 second, I need to import. Basically then I get a named vector where the name is the same as the column name and the value is the mean value in that column. the second question was determine the type of each column in the flights data frame. And again, I've sort of followed a similar structure. So assigned my data frame to this df variable just to make things easier to compare, created an output vector, this time of characters because types return a character. Same length as the data frame, i.e. the same number of columns. I've assigned the names of the columns into my output and followed the same thing. Instead of saying mean, I said class. And this gives me the following. So the month column is contains data of type integer, day column also integer, etc. Third one, computing the number of unique values. Here, same story, except instead of class, I used n distinct from dplyr. So if I run this, in the iris data frame, this column has 35 unique values, that one 23, etc. And generating 10 random normals from distributions with means of that. So I've basically put the means into a vector. So that's my input. My output will be a list where each element, I mean, I could, I think I tried to give a name, but I think names can't be integers or like numeric. So I struggled with that. I guess I could do like string representation of these things, but yeah, maybe that's something we can try. And I basically iterated through means, and then at each position, so seek along basically returns like 1, 2, in this case, it would return 1, 2, 3, 4. So the first position, this basically, output 1 will basically populate the first position, output 2 will populate the second position, etc. And I'm drawing a sample, 10 random normals with the mean as in the list and standard deviation of 1. So that's the result I get. And I've chosen a list so that each value could be could contain 10 sort of separate elements. Because if you do sorry, let me just check. If I do double here, even though each of these values is a double, because of the length parameter, it wouldn't work. I get an error because basically this has length 4, right? So this is an empty vector of type double of length 4. But what I'm trying to do is take position 1, and instead of replacing it with another vector, I'm trying to replace it with like another sort of double. I'm trying to replace it with 10 doubles, which is why I get this error. More elements supplied than that there are to replace. So I'm trying to replace 1 with 10, which is why using list works better. Any questions on the first question?
No, I'm good. I was just thinking about something like trying to name the vector means, or creating something like that, and probably could just use like a paste and add like a prefix or prefix probably before all those numbers.
Yeah. So like as character and then also put a prefix, or just put a prefix.
I think it should just be a prefix or paste note or something like that. Ugh. I can't
Let's try that.
think about it.
Let's first see what this does, but it should.
Yeah.
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 Yeah, that works with a prefix. That's mean minus 10, mean 0, mean 10. I mean, we could just put it there like that. I don't know if that's clear.
Nice. One question, by the way, something I haven't figured out. The pull function, is it in base R or is it part of tidyverse?
It's tidyverse. I think it's the same as doing $. So like if I do, what was this, like df that. Was it all or every? Actually, I think this was part of per as well. So we're sort of like using it before we. Okay, I'm going to do like a hacky way of confirming it. So I'm going to do sum where they're different. And if they're all the same, then.
That song, because it makes you feel like, I don't know, empowered to dividing. You know, I don't know, I really, really like it. So that's cool.
Let me just get the backing track.
Sorry, hold on. Is that from me? No. Havva? I think we lost your sound.
Yeah, one second, let me start sharing it. The pull function is the same thing as this $.
Clever.
Alan, are you still there?
Oh, yes, I'm here.
Ah, cool. Okay. Shall we move to question 2?
Yes.
Okay. We're then given basically a list of like a number of for loops and asked to eliminate each of the for loops in these cases. I think all of these are basically vectorized functions, so you don't need a for loop. So the str_c is already vectorized. So instead of iterating through each of the letters, you can just give it letters and then say collapsed is an empty string. This gives this gives what am I doing wrong here?
You have to call out again.
Ah, right, yes. Cool. So this and that give the same output because this function is already vectorized. And similarly, the standard deviation is already a vectorized function. So all you need to do is just do SD of X. And similarly, the random sampling from the uniform distribution is also a vectorized function. Sorry. In this case, what you're doing is basically calculating the cumulative sum. So we have X, and then I do, run this and then print out sum over X. So it's the same value as that. I like sum the number of times they're not the same. Although the problems with sort of near, yeah, no. So they're the same. There is no instance where this and out isn't the same. So this is another way of writing cumulative sum of x. Any questions?
No, that makes sense. Thanks.
I've kind of not done the songs because I just postponed them too much and I forgot. But yeah, if you want, we could like find, yeah, you do the song sort of examples as well. Did anyone have any like problems or questions about these?
Nah, no, I'm fine with this.
Yeah. I think
I mean,
actually
these
some-
questions are more like figuring out what the function is doing, basically, and trying to get another function in R that does the same thing.
Yeah, like finding where to put the for loop, like what to iterate through, I think. But yeah, I've not attempted that. And yeah, the same thing for the loops. I forgot to do this one as well. But if anyone had problems with it, we could sort of go through it. No, take that as a no.
No, I'm good.
Cool. So the next next section was about like the four. Oh, sorry, I just seen. Okay. The next section is about different variations of for loops. So typically the sort of the reason you write a for loop is apparently one of these four things. First is modifying an existing object instead of creating a new object. So you iterate through the object. Let's say if it's a data frame, go through the columns. If it's a list, go through the elements. If it's a vector, again, go through each element and change it, maybe based on some condition or, you know, recalculating something new. The second is looping over names or values instead of indices. This is kind of what I was doing earlier when I was iterating through names in my question 1 example, where I initiate my output vector, give it the same names as my input data frame, and then when I took like column name in names, as opposed to this later example where I took index with the indices of my column. The third thing is handling outputs of unknown length, and the fourth is handling sequence of unknown length. I think these two are, again, like less common than the first two, and in the book as well, like there are sort of more solid examples of these. So modifying an existing object, this is based on this function that we encountered earlier in the function section, I think, of like rescaling each column. And again, as I said, it's quite similar to what we did in the previous exercise, where we're modifying, we're basically taking our data frame and modifying what was our A column now with a rescaled version of the A column. So now column A is gone through this sort of function and updated. The second looping pattern of like iterating through indices is again a similar idea. So instead of like here, instead of iterating through names, we can also iterate through indices. Sorry, yeah, indices. And in terms of like unknown output length, the suggestion here was to, instead of appending and growing this sort of output vector time and time again, to just like combine everything in one place and then do the, accumulate everything in a list or in a vector, and then do the combining in one step, so that you don't run the same, you don't copy the existing values every time you go through the loop.
Yeah.
And yeah, examples with like flattening and unlisting were given here. And unknown sequence length, again, I think this is quite uncommon. A while loop is a lot more appropriate here than a for loop. And the example given was basically like how many times do you need to flip a fair coin to get 3 heads in a row? You don't know before you start how many times to try. So you can't really say, you know, for I in, I don't know, 100 or 300, because maybe it will take more than that. So instead you use a while loop where you just monitor how many times you already had heads in a row and stop when you've reached the desired number, which is 3 here. But yeah, this is not very common, and most examples that you need to use while loops would be simulations like this. So the exercises for this section was about, okay, the first one is, imagine you have a directory full of CSV files that you want to read in. You have their paths in this vector, and now you want to read each one. Write a for loop that will load them into a single data frame. So this is an example of, we don't necessarily know how many of them there are, and we want them all to be combined into a single data frame. So it's an example of the third pattern. And the way I've approached this was to put them all in one place. Sorry, from that. So I've used the code they gave in the question to get the file names, and I've created some like 2 sort of CSV files just to have something. And then I actually used map, but I guess I could have used like a for loop here. So basically for file in files, read CSV and then put it in the output. And then I did bind rows in this example. So basically my 2 sort of, I can actually, let me find my data just to show you. This is my data in file 1 and file 2. I basically have header 1, header 2, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, up to 16. So these are my 2 files. And when I read them, I get the first one and then the second one. So if I run just this is a list when my first element is my first file, the second element is my second file. And then when I bind rows, I can stick them together basically and get this output. Does that make sense?
Yeah, very neat.
Although I guess, yeah, does it say use, use the for loop. I failed to do that. I jumped straight to map. But if, yeah, we could try to write a for loop if you guys want to also do that.
Yeah, that would be interesting. I think I have an idea about how to do it. Until the binding, I need to decide whether to do it outside the for loop.
Yeah, so I think the idea is that it's best if it's outside, because basically here it sort of explains why. So if you do it inside the loop, sorry, let me find, yeah. Oh, if you do it inside the loop, in each iteration, R has to copy all the data from the previous iterations. So you end up with like poor performance.
Mm.
So if you had 3 times as many elements to loop through, so instead of 2 files, if I had 6 files, it would take 9 times as long to run. because of this sort of performance implication. And a better way to do that is to create this to collect all your output in a vector, let's say in a list, iterate through the thing you want to iterate through, in this case, files, do what you need to do, i.e. read the CSV, because this will give us the file name, right? And then save the result of that operation in this out. And then once you've gone through everything, and you have, let's say, in this case, a list of 3 items, each one of them with 100 elements, normally distributed, etc. Then all you need to do is, each one of them with a length n, which is a random number between 1 and I think 100.
Mm-hmm.
And then once you're done, put them all, stick them all end to end to get your final result, if that makes sense. I don't know if I've confused you more than explained it.
Yeah, I mean, it makes sense to me. It's basically the same thing. The only difference is that now here you're trying to bind the rows, bind the rows basically by column.
So instead of doing it with the map, actually, with as they're asking, with a for loop, we'd first create, let's say, we'd say, make a list, same length as files, and then, and then we basically iterate through the files. So for file, file name in files, will that work? Out, or we don't have names. So we can either make this out vector have the same names as the file names, or we can iterate through indices. Let's do index. Use the sec along. So basically this, remember we have 2 files, and this basically gives us 1 and 2. If we have 3 files, it will be 1, 2, 3. If we had 4 files, 1, 2, 3, 4. So basically like a sequence along this vector, which gives us the index. So the first position refers to data 1, second position data 2. And we want to keep the same index. I've lost the square bracket. Equal to read CSV or file name index. Right, this would be it. And then let's just print out.
Just another bracket.
Where, sorry?
Yeah.
Files, not right. So we basically get the first, the first file and the second file as in my input. And now if I do bind rows of my output, I get them bound together.
Yeah. Oh.
I don't know if there's any other way of doing that. I think this is a dplyr thing. R-bind? I think R-bind is the same thing in basic.
Yeah, that's the best R. Just that I think So bind rows is dplyr, so it understands the
Yeah.
but our bind is actually different.
Yeah, I don't know how to do it with rbind.
Nah.
I guess
Because with our bind you would actually need like another iteration or for loop.
it's not good.
That wouldn't be nice.
Cool. Is that, yeah, any questions?
No, I'm okay.
No, thank you.
So, second question, what happens if you use for, I don't know, name in names X and X has no names? I just noticed the change. Cool. And X has no names. What if only some of the elements are named? What if names are not unique? So I created an X, which is just 1, 2, 3, 4. And if none of them have names, as in this case, you can't access anything. So I tried to just like run this basically for name and names of X, print X of name, and I've got nothing, no output. If I give them some of them names, but not all of them, so let's say I give 1, 2, and 4 a name, but not the 3, and run through the same thing again, this time I get A1, B2, there's no name here. So basically, in the first iteration, I have NM is equal to A, and then X of A is 1, so I get A1. Next time round, B of X is 2, so I get B2. The third element is NA, X brackets NA gives me NA, even though the value was 3, but because there's no name, I can't access it like this. And then I go to the fourth element, which is D, and X of D is 4, so I get D and 4. If the names are repeated, like so 1 and 4 have the same name, run that and run the whole thing again. This time, I basically get the first match. So A matches both 1 and 4, but because 1 happens before 4, I get 1 again here. So if you're going to use names, make sure the names are unique and the things that you care about have a name. Any questions?
No. So basically, this is the same as if you're to follow the indexing for lists. Basically, the same concept.
Yeah. And I think we had a similar thing also with vectors in your presentations. Remember, if like NA and null and infinity, I remember there was a like similar complication around then. Like if you access something with NA, you get NA even if the value isn't itself NA.
Yeah, that's true.
Question 3. Write a function that prints the mean of each numeric column in a data frame along with its name. For example, Iris should show this. So also it says extra challenge, 4 functions I used to make sure the numbers lined up nicely, even though the variable names had different length. So for this, I start with looking at the maximum length of the names of this data frame so that I could have the padding necessary later on, which will become apparent. So first I define max length, which is this longest name. And then for each column name in the names of the data frame, first of all, I check if it's numeric because it says print the mean of each numeric column. So if this column is numeric, then print something. And if it's not, so if this if statement fails, then I don't do anything. So if the column name or like the value of the column isn't numeric, don't do anything. But of course we could type here, like, I don't know, else print not numeric or something like that. But yeah, so if the column is numeric, then I print the following. So I combine the column name padded to the maximum length so that they are all aligned the same way.
Okay.
And then the next thing is looking at the mean, which is what the question is asking. So take the mean of that column. And also I noticed these were rounded to 2 decimal places, and I did round to and as character. I don't know if as character is needed, but I did that anyway, which gives a very similar output. I don't have the 0 that they have, so I'm not sure what I should have done there, but pretty close. I've aligned them on the left-hand side. I guess I could do like right adjusted, but the numbers are aligned. So that was my solution.
I think I'm thinking that the 0 comes in because you use round, and maybe if you use something else instead of round, one of those other functions, then the 0 will show up.
Was it trunk? Let's try trunk if that was.
No.
But it wasn't.
I've forgotten the one that gives you the number of significant places.
Yeah, I don't know.
But yeah, should be one of those.
But you know, close enough. Yeah.
And so if you remove the character as the character, yes, I think then we won't have the quote. Still comes up.
Is it message? Do I need to? Is that right?
Okay.
Returning mama.
Okay, but I think I get the point. So instead of printing or returning, then you just print. Or is it cut?
I don't know. And then I need
The new line.
new line between them. How do I do that? Here. Is there an end argument? No. Let's try.
Let's see. All right, so basically with cut, let me send you this. It's just one string, but with // n. Like that.
Yeah, but in this case, if I like, it's not the separator, is it? Because that's this.
Yeah, it's not. Yeah, it's not a separator.
Oh, okay, I could just put it here. I could put it that. Oh, one second. Well, I think
Should be able to work because. Okay, let's see print.
I just want to see if this is working still. Yeah.
Interesting.
It's now putting this separator between those as well, which is a bit annoying.
Yeah,
So,
could you print the the slash n after the separator. So get it from there and put it after the string underscore c.
No, but is that?
Okay,
Let's try that.
probably after separator.
So here,
So
I don't think that will work. But
no, none that outside that bracket. Same line, but outside the bracket.
like so.
Yeah.
Okay.
Oh,
Cool. That's one step closer.
it's really a weird syntax actually with this. Okay, I see. Now I see what it's doing. Hmm.
Yeah, I think close enough.
Yeah.
And question for what does this code do? How does it work? So basically, trans is a list of two functions. The first function just multiplies the value by this constant. And the second function turns it into a factor with levels auto and manual. And this list of functions is a named list. So the first function has the name disk, the second function has the name am. And when you, in the for loop, we're iterating through this list, through the names of the list. So basically, in the first iteration, var is equal to disk. In the second iteration, var is equal to am. And in the body of the for loop, we are basically taking the function inside trans of given with that name. So when in the first iteration, when var is equal to disk, we go into trans and take the function in it, or take the element in the list called disk. So that gives us this function. And we apply it to empty cars of the same name. So what we're saying is basically, go to this data frame and change the values of these two columns. And how to change them, like the instructions for changing them, is in this list. Mm-hmm. So basically multiply the values in the disk column by this value and turn the am column into factors. And everything else, don't change anything, because basically we've not touched them. So that was my thought. And here, instead of doing it in place, I did it separately so that I could look at the difference. So this is the original. So basically I'm printing it here, empty cars, which is the data frame we looked at before. And after we go through this modification, you can see that if you look at the disk column, we go from, let's say, 160 to 2.6, which is the result of this multiplication. So the disk column we have modified according to this instruction, and the am column is now a factor with levels manual and auto. So where it was 1, it has become manual. Where it was 0, it has become auto.
Nice.
Shall we move on?
Yep.
Cool. So this is the section where we are introduced into functionals. So these are the ways of doing the same thing in a more succinct way, as opposed to for loops. So like the example before, where we have this data frame with 4 columns, each of them with some random numbers in them. Here's the example of finding the means of each of the columns using a for loop. And then there's a bit of like discussion around, if you wanted to do the same thing for median, you'd have to copy this, paste, and change just the function name here. Instead of mean, it's median, everything else is the same. And if you wanted to do standard deviation, again, copy paste, but this time just change the function and everything else remains the same. And if you were to just look at this code, you would find it very difficult to sort of quickly say what was different between them, because there's a lot of sort of boilerplate code before you've actually seen the difference. So using functionals, for example, map, would make it a lot easier in this case by highlighting what's actually different between them. And yeah, some more examples of like how you can, like write things in a more succinct way. And if you use the map function, you can turn basically all of this into a much more sort of easy to read way. And if we had to sort of rediscover a map function ourselves, we could, for example, sort of summarize it like this. So the above these copy paste function took a data frame as their input. And if we also wanted to write a function that took this function that was the only thing that was changing between them, mean, median, standard deviation, we could define like a meta function, the sort of column summary function, which takes the data frame and the function that we want to apply, and keeps the boilerplate code. And where before there was mean, median, standard deviation, we now have this function argument, which is an argument of this meta function that we've defined. So then if we want to do the same thing over and over again, we can just change what was different between them. And it makes it a lot easier to see what's the same and what's different between each of these different runs of the same, like very similar code. So this is us like building what the map family of functions do from scratch. And I guess apply, but I'm not very familiar with base R, so I've gone, from for loops directly to map.
Yeah, just a quick question, Havva. This meta function, something I didn't understand was the fun function here.
Yeah.
Like you don't have to define anything else. Someone just writes median and carried on by the function.
Yeah, so what's happening is basically we are very familiar with functions taking arguments, and these arguments being objects like a data frame or a number, an integer, a character. Like if you wanted to, let's say, I don't know, find the string distance between one variable and the next, it's very easy to imagine to write a function which takes these two strings as its arguments. But if you're thinking in terms of like functional programming, just like a data frame could be an argument to a function, or a string, an integer, you can also have a function be an argument to another function. So functions can operate on other functions and return values. So this fun is just the name of the function, but it could be anything, as long as that function can do what you're trying to do here. So in this case, can operate on the column of a data frame, whatever that column might be, then it will work. So in this case, our data frame contains only numeric values. So in place of fun here, we can put anything that will work with numeric values. We could even put, as dot character, if we just wanted to turn everything into character, or I don't know, like to take the first value, take the last value, etc. That makes sense?
Yeah, nice.
So this is basically like discovering the map family of functions from scratch. If we wanted to sort of make this code easier to read, we'd write a meta function that takes our input and the function we want to apply it, while abstracting basically all the similarities between them into this meta function. And yeah, so like the map functions provide further help by basically also dealing with type. So just the bare map function takes an input, iterates through it using the function that we provide, and gives as an output a list. But there's also these variants which turn it and coerce it into logical, integer, double, or character. And we'll sort of see examples of this when we are converting our first exercise to use the map functions. So there's nothing wrong with just using map, but if you're then going to convert everything into, let's say, logical or integer, then it makes sense to use these functions because they check for these sort of types. So just like our example before with the 4 columns and 10 values in each one of them, since we expect the mean to give a double, we can just do a map underscore double, and it gives the same output. So what we were writing beforehand, basically, this meta function was actually map double because we hard coded the type of the output to be double. But you can imagine there's another flavor of this function for, let's say, just logical vectors, where you would, instead of double here, you would put logical. And there's another flavor of it for character vectors, where you put character. So these are the differences between these different versions of the map function. And again, if you're dealing with numeric values and you expect them to be doubles, use map underscore double. You can pass any extra arguments that your function takes just after you've written the function. So basically, this is the same thing as saying for column in df, output of that column is the mean of the column, and then trim equals 0.5 inside that mean function. So you iterate through the df, and then any extra arguments that this function takes, you can provide. Any questions?
No.
There are also some shortcuts that the per package sort of enables. The first of them is basically writing an anonymous function using this tilde. So instead of, so here basically we're saying take empty cars, this data frame, split it based on this CYL cylinder column. So what that means is take all the values, so take all the rows which have cylinder value 6 into one data frame, and then all the columns with cylinder value 4 into another data frame, all of them with 8 into a different data frame, etc. For each distinct value of cylinder, split this data frame. And then this will basically, I guess we could just like run this and like follow it just to get a better understanding. So if I run this, I basically get 3 data frames. One of them with cylinder values 4, the next one 6, the next one 8. So these all have values 4 in cylinder. These have 6. These have 8. And then, so I've gone from having one data frame to having a list of data frames, list of 3 data frames. And then I want to apply a function to each of these elements, so each of these data frames, right? And the function I want to apply is to fit a linear model where MPG is described by WT. And the data is this data frame, right? The data is whatever the function takes. So instead of defining this anonymous function, I can also just write this simply as just like dropping this definition with a tilde, and everything else is the same, except the df, if I didn't change anything, wouldn't have been defined, so I'd get an error. So instead of like what the function takes is then replaced with this dot. So the dot means the iteration that I'm at, you know, is the data input. I don't know if that makes sense. Like the map function basically iterates through this list of 3 data frames, and each iteration, the dot refers to the data frame of that iteration. So the first time, the dot will refer to this data frame. Then once that's done, it will refer to this data frame. and then it will refer to this data frame. Does that make sense?
Yeah, so when I was going through this, I was a bit confused originally because I thought there was a difference between .x and dot. But
So was I.
sorry?
So was I.
Yeah, but I realized because I kept on running different things with dots and .x, then I realized it's the same thing actually.
Why has it got .f in the paragraph? A few shortcuts that you can use with .f. I don't understand why that.
Yes,
Is
so that refers to the function. So map basically takes the first argument is the
.x.
yeah.
Why are the dots there? Why has it got .x as well?
Yeah, I think it's for them to make it to have a convention for the function.
Yeah, and
So,
also like not to like f and x are used to mean like other things in other functions. So this is just to make things like clearer.
yeah, for the map for the per function.
I think. Yeah.
All right, okay. So that's where I'll
basically,
find it in anything to do with map or per.
sorry?
So that's the place where you'd find .x or .f is just things that are to do with map.
Yeah, mainly, yeah.
Yeah, and map is part of per.
Okay. Thank you.
No worries. Yeah, when I was going through this, I thought I understood and there was a difference between dot and .x, but I guess we could just like try and find out. I think there is a difference because I think .x is the list, whereas dot is the current iteration, but let's try. If I comment this out, this is the original thing here. So split it into 3, and then for each one, fit a linear model where this is explained by that. And we're saying, instead of defining this anonymous function that takes, let's say, df as the argument, and then we iterate through df, instead of doing that, a shorter hand of writing that is just using tilde. So we're saying an anonymous function, basically take this and apply the function of a linear model. This is explained by that, and the data is the current iteration, and this gives the same output. Now if we do .x, I think this should fail, but
No.
we get the same output?
Yeah.
Yeah, okay, well, they're the same thing.
Yeah, I was surprised actually. It was like, really? Why do we need them?
Yeah, it refers to the current list element. Cool, and you can again do the same thing. So you can save this as models and then apply summary to each element. So we're going sort of deeper and deeper. So take empty cast, split it by cylinder, fit a linear model. Then now you basically have a list of linear models, right?
Yeah.
Then next, take your list of linear models and to each one apply summary. And then next, take each summarized linear model and extract the r² value from it. And again, this is quite a common operation to do. So this is also, there's also a shortcut for this. So whenever you're saying, take the current element and then extract this property of it, instead of writing this, you can just put the character, the string of the property you're interested in.
Okay.
Which again is shorthand for writing all of this. I think there's a question of like, it is like there are fewer characters to type, but which one is more explicit or like easier to understand, I think is still a question to answer. And again, if you're familiar with this shortcut, then sure, this is a lot easier to read, but if you're not, then it's not.
Yeah.
Yeah. And it's basically then comparing these functions to the base R equivalents. But basically the per functions are more consistent. They behave in a very similar way within the per sort of family of map functions. And also they support this different output intrinsically. So we're sort of focusing on that. And I suggest maybe we go through this first exercise, because I'm conscious of time. We go through this first exercise of converting the for loops that we wrote in the beginning of the session into map functions, and then continue with the rest next week.
Okay.
So first question. I've also copied my answer to the first part just so that we could prepare. So instead of writing all of this, what we basically want is, if we want to calculate the mean of every column, we basically want to iterate through data frame, empty cars. So that's our .x, the thing we want to iterate through. And the function we want to apply is mean. So this gives the same result as that.
Yeah.
And it automatically preserves names. So here I was doing this extra step of setting the same names to my output as my input. I don't need to do that either, because my data frame contains names, as in column names. They are kept here. Similarly, to get the column types, this time I'm expecting a character, and I've written a character there instead of a double. So I'm using map character as opposed to map double, giving it the thing to iterate over, which is a data frame, and then what function I want to apply to each column, which is type of, and I get the same output. And finally, number of unique values. Again, I'm using n-distinct like I did before. And because I'm expecting a double, I use map double, and I get the same output as before. For generating 10 random normals, we'd use the list. So I'm using a bare map, which automatically produces a list. And the function I want to apply is rnorm. And any extra variables that I was given before, so n equals 10, and standard deviation equals 1, instead of writing it inside like this, I just add it separated by commas. And if I had I basically get the same output. That's it.
Yep. Nice. One trick actually I've got, which I wasn't aware of, is just adding the extra arguments of the function that you want to apply.
Yeah. So shall we stop here?
Yeah, I'm fine. We can stop here, then we continue next week.
Okay.
But then can we stop the recording for now?